So we're going to work a couple of demos into this talk for reasons that will become clear very shortly.
Yeah, so before Joe starts talking here, I'm gonna make an Urbit here download a 130 megabyte file using old Ames. And the reason I'm doing it this early will become apparent. Oh, and there will be a stopwatch here. It's a little bit small, but you guys can follow along.
So I'm going to talk to you all about, as Ted introduced it, the largest core development project in the history of Urbit.
In the last decade.
In the last decade. Right around a year ago, Ted asked me to work on Ames routing, which works really quite well most of the time and is occasionally, inexplicably, totally flaky. We would get periodic reports of ships taking hours to send a hi. No, it went to sleep. I'm going to have to just stand here and massage it while I. This won't be a problem. I have close to 100 slides. We'll be going quick. So my reputation, I'm sure, precedes me in terms of scope creep, and everything that I'm going to show you here today is done except the routing. In August in Wyoming, I gave a much shorter version of this talk at reassembly, and these were the subtitle, the punchline, the priorities that we're aiming for. So let me talk a little bit about the way that current Ames does not accomplish these things. We already mentioned that routes are flaky. The peer discovery, this is a combined problem of how you discover peers and then how you forget them in an unprincipled manner. The topology just sort of moves around for no reason in a very, very dumb way. Classic case of stop hitting yourself. And then, of course, another stability problem is one of many cases, but network performance just falls off of a cliff under load. Ships become unusable. People use dedicated moons to distribute applications, to host channels, and so on. The legibility is effectively nil. The metadata in the packet is only enough to kick off the authenticated encryption that's used to authenticate the data and protect it. And debugging Ames is an exercise in pain that Puri could tell you much about. So these are some of the goals that we baked in on this front. You need to be able to, from outside the system, in addition to inside the system, observe and monitor what's actually going on. It has to be viable to debug the system. Once the data flows are legible to the outside world, you can provide value-added network services. You can do things like quality of service enforcement that you just can't do in current Ames. And then there's a whole host of possible external integrations, the often discussed, lib-Ames style third-party integration, which people have heroically done, but it was 75% of re-implementing Urbit in Go or something like that. Completely insane. And so we came up with a way to deliver these things. And then, last but not least, But those weren't the design criteria that we used in this effort. We didn't sit down with a list of features and say, we have to, by hook or by crook, get these things into the protocol. What we did was much, much dumber. This was the entirety of the design principle of this effort. And this throughout the process, paid unexpected benefits over and over again. So I'm going to try to talk about, in some detail first, what it is objectively that we have actually built, and then some of those surprising advantages, the lessons that we learned from them, what you can expect from this. Taking it from the top, we started from scratch. As Ted said, we have rebuilt the entire stack. And so you can now forget everything that you know about Ames, and we'll build it up from here. Again, everything's pushed through the namespace. So we have 3 packet types. You can request to read data from the namespace. You have to be able to write too. So you can request to write data, and there's 2 paths in that request. The packet is a poke, right? But the payload of that poke is data that you have bound in your own namespace, and the party that you are poking with that data will acknowledge, positively or negatively, the result of computing over that payload in their own namespace. So you always have this binding of path to value, and in the case of poke, it's bidirectional. Both of those are request types. There is a single response type to either one, which is a binding of data in the namespace. And that's it. That's all you get. To realize those, we implemented codecs in Hoon and C. One of my favorite pieces of code that came out of this effort was a framework for delaying the serialization as long as we possibly could, building up this tree that kind of specifies in a miniature DSL the actual serialization we want to do, and then doing it all at once in a jet where we can amortize the allocation. That's a problem that has eluded me for years working on this kind of code, and so anybody who's curious about that, I'll talk your ear off about it. But then, of course, we implemented these packets in C, these packet formats in C as well for reasons that will become clear. We also implemented a bunch of new crypto, and in fact, we rolled our own. So first off, let's see. We haven't touched azimuth. Your azimuth keys are still ed 25519. The asymmetric crypto remains the same. The signatures remain the same. But current Ames crypto dates to, I believe, 2016, maybe 2017. And it used, at the time, the cutting edge deterministic authenticated encryption, no nonces, very elegant design, a construction called AES-SIV. But a major downside of AES-SIV is that it requires 2 full passes over the data. You generate your nonce basically by hashing the data, and then you do another pass over the data to encrypt it. And throughout this effort, we were looking to remove any cap that we could find on the scalability of the protocol. And so that was a real bummer. Walter Parter, who's unfortunately not with us today, did the bulk of this work, in particularly combining Cha-Cha, X-Cha-Cha, and the Blake 3 stuff that I'm going to talk about into, I believe, a unique construction for authenticated encryption that's, easily twice as fast as what we were doing before. None of this even bears on like the normal Ames performance stuff that you're talking about. We're in a totally different level when we're talking about this kind of performance, but we were really trying to remove all of the obstacles that we could. We used Blake 3 because, first of all, it is the fastest cryptographic hash by a mile. It's an amazing work of genius. But also because it just is a Merkle hash. and I may get into this later, I may not, we'll see how the time goes, but prior revisions to the Ames protocol have paid huge penalties in performance when it comes to authenticating data. And we wanted to de-emphasize packets very much so throughout this effort. We wanted the protocol to be message-oriented. We couldn't find any other way to envision transport agnosticism, but it also just stemmed from our maxim of pushing everything in the namespace. What is in the namespace? Well, there is a binding from a path to a value. That value is the message. That's the data at the unit that you care about it. That's the data at the unit your application works with it. The packets are just a means to an end to getting you that data. So we really don't want to, for instance, sign a packet, which is something that we were forced to do in prior constructions. And so we searched far and wide for an alternative, and what we found was clever applications of the internal hash tree from Blake 3 to incremental construction, validation, delivery of Merkle trees. And what's amazing about that is the constructions nest inside each other, right? So when you're going to sign the data, you never actually, it's computationally unfeasible to sign like gigabytes of data. What you do is you hash the data, you sign the hash. And so by virtue of having a hash that is also internally in its own construction a tree, we could sort of zoom in and out of the pieces of the construction that we're coupled to here and then link together. This is going to be brutal. Chain together the provenance of the data authentication that we're performing. And as far as I know, the application of this to networking is entirely novel. I'm realizing now I have like a tense disagreement in this, where I'm jumping back and forth between like negativities of the current system and positivities of what we've replaced it with. My apologies for that. In this new protocol, in directed messaging, our publishers are completely stateless. They're implemented as a hierarchy of recursive overlay namespaces, which makes it incredibly elegant because you're talking about very small, pure functions composed very naturally. And that can be made efficient because we persistently memoize intermediate results. This has been a problem that plagued Ames throughout its entire history, is you transactionally and durably commit to the ephemeral partial results of delivering a message. So you're managing these packet queues. You don't really care that much about packet queues. You care about the message, but your state is blown up because of these packet queues. Or you'll do very computationally expensive things to try to deduplicate the package queues. It all goes away here because what you store is the data as you actually care about. That's all you do. The data lives in your system somewhere. You made it available in the namespace. That is its canonical form. Everything else is a pure projection of that. You don't want to recompute the projection every time because that could be quite expensive. And you want to keep it around, but you want to do that in an informal manner without actually committing to it under Arvo semantics. The clients, on the other hand, these are a layer of state machines. The clients are stateful. The clients have to be stateful. The directedness of this protocol shows up in many different ways. There's request response, right? There's the symmetry of the routing. But the end result of all of that is to put the onus on the clients. And this may seem surprising, but I'm convinced that it's the virtuous and proper, righteous thing to do in a peer-to-peer system. Pareto distributions are going to show up in arbitrary places in the network. You don't know what will be popular. You don't know what will be successful. And unless you can put the load, you distribute the load throughout the clients, the work of retrieving the data being primarily the responsibility of the clients, you recreate the incentives, in a small part at least, that got us to the point we're at now. Sadly, this means that this part of the system is not quite as tiny and diamond perfect as it was when I envisioned it. The nice layering between messages and packets and the various entry points between them. When you're a state machine, you end up with sort of the Cartesian product of the entry points there. They do not linearly compose the way that the overlays do. So this is the heart of what we focused on. This is the value add that we'll talk about that enables this to not be the case.
It's not even close yet, so don't worry.
Okay, I was just checking. Got to keep doing this. I'm going to have to start going faster here, too. So the next thing that we built is we took those one of the state machines that I just talked about that are nested in the vein, and we re-implemented it in the driver. This receives response packets, makes requests for subsequent packets within a message. It performs its own congestion control and depacketizes. And this is where all the speedups live. We took we have de-emphasized the packets. What we need to authenticate about the packet is its existence and position within some larger message. But like I said, we don't want to sign it. We want to do as little with it as possible. It's just a slice of a message. The Merkle tree elegantly allows us to do that. And so the responsibilities of this state machine, besides the re-request, retry, congestion control obligations there, are to validate the packets against the Merkle tree, incrementally construct the Merkle tree, validate the packets against it, assemble the message, deliver the message into the loop. We do not churn Arvo's event loop for packets. In summary, we wrote a new vein, implements publisher namespaces, client state machines, stores routes. As Ted talked about earlier, live per peer migration between the old Ames protocol and the new Ames protocol. For the first time in the history of the project, that has been made bidirectional. That's not operationally interesting in the long term, but it's a pretty massive flex. I get to say that because I didn't do it. Thank you, Jose. And it lets us get this on the live network much sooner and test it much more aggressively. The driver for the publisher caches the responses of these overlay namespaces, and it can prefetch into those caches. It implements the client state machine, and it implements the stateful relaying protocol from NDN, what we call symmetric routing. And so from outside, especially when you're looking at this from the perspective of the runtime, or you're looking at Wireshark or whatever, it's just a new protocol. It's a different packet format, it has different semantics. It's just another thing. The runtime knows how to speak the old protocol and knows how to speak the new protocol. It's not super interesting. And from the inside, you don't have to do anything. If you're writing Gall agent, you send pokes, you send subscriptions, hopefully not for much longer. You make requests from the namespace. Everything's the same, but better. Let's see how we're doing on time. I don't have a clock up for some reason. So that's what we built. That's all real, that exists. Like I said, the symmetric routing is sort of the least real part of it, but that's real, and we'll show it to you if this ever finishes. The way that we got there and the way that we convinced ourselves that this was the right direction for Urbit networking overall involved, as usual, going back to the foundations and reviewing any prior art that we could find. And so I'm actually going to take a poll of the room. Who here is not familiar with NDN? If that doesn't mean anything. NDN, named data networking. Thank you. You can put your. So what I have here is shamelessly ripped from the creator of NDN, his whole history of networking and how he came to invent NDN. When Curtis introduced Urbit to the world, he cited this man's work in a way that grabs your attention. And in fact, I believe that this content-centric or named data networking is really the inspiration for the Urbit namespace. Otherwise, you can't really imagine someone committing quite so hard to like fuse. And I'm going to see if I can blitz through this. The thesis of the named data networking project is that networking itself has had a success crisis and needs to be refounded on different principles to scale into the future. Now, the talk that I'm cribbing from here was given somewhere between 15 and, 18 years ago. And the author works at Google now. So it's quite possible that they're doing this internally, but this has not. The thesis should be viewed with some skepticism because this has not happened, and the internet has continued to exist. But very briefly, networking was originally telecom. It was all about wires. It was all about direct connections. You established a physical connection between the parties that were to communicate, and then you only sent the data that you needed to send. Addresses, routing envelopes, all these other kinds of things would have been a shameless waste of space. And of course, everybody's at least loosely familiar with the history. The ARPANET came along, packet switching came along. And Generation 1 was entirely superseded by Generation 2 that cared not about the connections, but it cared about the endpoints, put a bunch of metadata inside of what you were communicating with, and unlocked massive degrees of freedom and how data was sent. Anybody who received the packet could forward it along on its way, contribute, and they used and abused the wires to the point where now what little vestiges of Generation 1 that still exist are actually virtualized on top of Generation 2. Like the phone network just doesn't exist anymore. It's all the internet. And so then as an evolutionary completion of this process, he proposes that Generation 3, to replace the previous paradigms entirely, will be focused on data dissemination, not conversations. So now I think we'll just skip a bunch of slides. So these are the problems that the named data networking is designed to fix. Interestingly enough, it's not clear how many of them are our problems, to be clear. But connected as a binary attribute. The internet is one thing. You're either connected to it or you are not. Establishing the connection is heavyweight. This is certainly still true, although notably not so much on Urbit. The network hates things that move, and nobody uses broadcast in a public setting. But the simplest way to think about this is that everything on the internet is basically a conversation between two parties. Anything that you want to do that is not a conversation between two parties is awkwardly, painfully, and expensively, simulated through a series of conversations between two parties. And the second point must be just exponentially truer today than it was in 2006. What do people do with the internet? They acquire named chunks of data. So Indian just inverts the paradigm. You can, of course, have conversations. Conversations are important, but conversations are expressed on top of this dissemination of data. So, I ask you for the next thing you're going to say to me, and you ask me for the next thing I'm going to say to you, and so on. Yeah, those are obvious enough. Just got duplicated. These are just the same points in more detail. I don't know why. Something I didn't realize, an advantage of this framing I didn't realize before I prepared this talk last year. Forcing data flow through the request-response straitjacket puts control over congestion events on the side of the conversation where you can do something with it. So, typically you think of networks in sort of a, hub and spoke model or recursive layering of hub and spoke models. And where you are when you're asking for data, you're on the fringe, right? The network is not by any means the most capable. And so congestion is not going to occur as your request flows into the core networks. The core networks can handle much more than you can. Congestion is going to occur coming back. The transition from the core networks back to the link as the data flows back to you. But when you're in a request-response paradigm and you have to ask for the next thing, right? The interactions themselves naturally sort of delay, those congestion events. Congestion events delay responses coming back to you. You are the party who will react to them, and that composes into a positive feedback loop where your adjustments actually affect the result. Whereas if the data is simply being pushed from the core to you, they need out-of-band signaling to react to those kinds of problems. In the packet switching paradigm, no, that's not the way to read that. In the telco paradigm, the source and destination was implicit in the link. Packet switching made that explicit in the data. That created the internet, that move. In the packet switching paradigm, time, sequence, and integrity are implicit in the connection. They're implicit in the conversation. Dissemination makes them explicit in the data. So this is a part of the conversation that Ted and I, in particular, spent a great deal of time discussing. We looked, 2, 3, 20 times before we leapt. This was quite some time ago, and it hasn't taken the world by storm. It's a very compelling story. How can we be sure it's not the wrong direction, that there isn't some other paradigm? If we're going to make an effort of this scale, if we're going to replace the network, we're going to double down, right? We want to be sure that we're not chasing something that already failed. So this is my own editorializing here. These are my best guess as to why named data networking, which it does exist. The protocols exist, implementations of them that you can run exist. And I believe that things much like it, information-centric networking, content-centric networking, there are a variety of umbrella terms depending on which government agency they're getting their grant money from, why they have not taken off. The compatibility story that's offered in the NDN design documents is that you can take TCP/IP and run it over NDN. You can take UDP and run it. You can run anything over it. It's a network. We'll underlay the existing protocols, and that's how we'll grant adoption. But that story sucks and it's backwards. Because anybody who's happy with the thing that currently exists has no motivation to, bite the bullet on engineering risk, operational risk, any kind of expense, where the best case scenario is that it keeps working.
You mean like Netflix? What about Cloudflare? Or like anyone that does like Edge or sort of like CDN type stuff?
Yeah, so for them to use a protocol like this, the clients have to upgrade. They can use it internally. That's what I mean. I believe that some data centers are using things like this internally, and some of the cloud providers are using it in their own internal implementations of their services. But to really reap the benefits, this needs to be end-to-end. It needs to be primary. You can also lay NDN over existing protocols, but depending on the protocol, the tension there could be substantial. Like, doing it over TCP would be, well, actually, we'll get to that. A real sticking point, though, security protocols themselves are conversation-oriented. There is not much that I can find in the way of research around multi-party communication flows, secure multi-party communication flows that don't devolve into N or N squared conversations. And the crypto actually works out that way. So many of the advantages here of explicit, referentially transparent request response are dampened very significantly if you actually have to republish the data for every single person who's part of the conversation. In simple terms, you're never going to get a cache hit. I don't believe that is intractable, that security itself means conversations. But little work has been done in this area. This one, though, will hit very, very close to home. It is not easy to use a referentially transparent namespace. It's actually quite difficult. The onus being on the client is not simply like an implementation detail of the layering of the protocol. It's conceptually inherent. You have to know what you're asking for. It's not my problem to educate you. And so, a place that this has shown up over and over again in very practical terms for us, I can't put too fine a point on it. We shipped an NDN protocol a year ago. Initially, it was only for public data, and the only use that it saw was for OTA updates, where the data is already public, it's a natural use, we can wire it in automatically. It took some nice load off of the handful of infrastructure ships that are primarily serving updates to the network. Now, of course, there's the small detail that the initial release was quite buggy, and people who tried to use it got burned pretty badly by that. We have made amends. We run everything ourselves first. We don't ship anything that's not actually being used. Anyway, you're all probably aware of the mini process changes that resulted from that. But once we got past that initial hurdle, the problem that everyone had was, how do I discover what the latest version is? How do I know what's out there? How do I get started navigating this space of referential transparency? As Edward likes to call it, the frontier discovery problem. There is not any one solution to this problem. Once you're anchored in space, right? Once you get started, you should be able to walk relatively based on version numbers and things that you already know. But even that can be very awkward depending on the format of the data. We plan to, after this protocol, release something called Pine, oft discussed, which lets you just ask the endpoint, what is the latest version right now? This is a non-trivial concession to reality. That request is not and cannot be referentially transparent. If you're going to cache it, you're going to introduce cache invalidation problems, cache control, hence down the rabbit hole you go. But the network is small enough, and that model of interacting with the data is intuitive enough that it doesn't seem worth standing on ceremony to reject that. But long story short, without that kind of primitive, what people have actually done in order to use this kind of protocol is start out by having a conversation, have the conversation to orient themselves in space, and then if the data is big enough to justify it, route around and go get the data. And so, that works and it's fine, but it's a really, really uninteresting use. It's like, I don't know if any of you are old enough. I feel like these things don't exist anymore. Maybe it's just because the internet was really slow. But there were like download manager applications and then like browser extensions, and this was like a thing that you thought about. That's what it feels like. It's like, this sucks, honestly. It's not interesting. So in this draft, we've, bit the rest of the bullet, eaten the rest of the elephant. Choose your own analogy. And we've moved the conversations. We have done what I described and put the conversations into the namespace, overlaid onto a dissemination network. So the rest of the advantages here you will get automatically. But that's a small fraction of what you can get if you can fully leverage the end-to-end referential transparency, because you're still having the conversation. That reference is the 37th message that Stuart is sending to me in this particular channel, encrypted to my key. Like, no one else is going to ask for that ever again. There's a lot of alpha left on the table. And so I theorized here and still maintain that new application paradigms are required, are mandatory to be able to leverage these sorts of patterns of, group, multi-party, hierarchical, incremental kinds of interaction. And it just so happens that you're going to hear about those tomorrow. The last two, whatever. If you search NDN, any buzzword that you can think of, you're going to find 20 papers. It got into the universities. I don't know if it'll ever actually come out. I use the name when I talk about the details of the protocol. Otherwise, it's not really interesting. I think those things themselves are a dead end. I think what we have shipped is already the largest public real-world deployment of a named data networking protocol, and what we are about to ship shortly will blow that out of the water in usage terms, and I don't think we'll ever go back. And of course, NDN itself is just the network model. It has an uneasy schizophrenic even relationship to referential transparency. It does not have a node model. It does not have a PKI. It is bring your own PKI. It has a totally insane generic like meta layer for how you do those things. We don't have those problems. It is all, because it doesn't have a node model, it is committed to content-based routing. So the way that the routers work, the way that your routing tables are built up, they have path prefixes. And a path prefix tells you what network interface you go at. And if you don't have a path prefix, you send it on all the network interfaces, and you just bootstrap the knowledge of the domain. It really wants to be the entire network. It's really cool. It's really hard. We don't have that problem. We have a node model. We have a address space hierarchy. We have an identity system. We can build a spanning tree. We can have our cake and eat it too here, right? We can maintain the semantics that data has a name, not a location, and also say, if you don't know better, the best place to start when you're trying to get the data is the person who published it. Amazing. See, seems really obvious. So now we'll run through, this part of the talk is a bunch of complaints of why all the prior drafts of these things were pretty terrible. This one's fun. Like I said, you really, really do not want to sign every packet. The long and short of this, the takeaway that you should have is that Finet, the Indian protocol that we shipped over a year ago that we use for OTA updates, takes the load off publishers for content that will be requested multiple times. For everything else, it's actually more expensive than Ames. So here's the design now. This is back when it was still a design. Ames. I guess I should bite the bullet on the meta digression at this point. We go back and forth over whether Ames is the Urbit network or Ames is one particular protocol with very particular semantics within the broader suite of the Urbit network. That equivocation has continued throughout this effort. We did all of this development fresh in new environments, new veins, new I/O drivers, all these kinds of things. And then we looked at how to migrate it and said, oh, this is going to suck, and we jammed the whole thing into Ames. So this is how Ames was always introduced in the past. This is the standard trifecta. Lately, I've been calling these Ames flows, right? In particular, these are pokes, where they work quite well. These are subscriptions, where they're an ungodly abomination. But we can't lose this. These properties are essential for some class of applications. They are essential for pokes. We'll just keep moving on from the... So again, in this theme of constantly reiterating, we are deprioritizing packets. We don't care about packets. Packets are a means to an end. The reason that it's notable that it is to be celebrated that packets don't churn Arvo's event loop. We do not want them to be transactions. You want download resumption, you want efficiency, there's lots of things that you want, but you just don't want a durable, permanent, forever commitment to having made it 1% of the way through the next word of this conversation. It's just not useful. Again, on the application model, we work very, very hard in old Ames to deliver a whole host of invariants to you, and then Gall just drops them on the floor. This is the legibility stuff I already talked about. I don't know where I'm pointing this thing. I've told this story before. It sounds really dumb when I explain it. It's the God's honest truth. This is actually how we got here. We sat down and said, All right, how do you have a conversation over a dissemination network where all you can do is read? And so you have to do this song and dance, and you proliferate the number of interactions, and I ask you to acknowledge the last thing I said to you, and you have to realize informally, externally, because this is just a read, it can't change your state. So something outside is like, oh, hey, you're asking for something that doesn't exist yet. Let me go and react to that fact. Like there's a hint there that I didn't hear what you said. Let me go ask you what you said. And so it's like the whole conversation, starts backwards. But we did that. And then once, I thought I had a slide. I have a slide here somewhere that's got the, yeah. And then to get out of the trap there, we just started pushing things together, right? So the write packet, the poke packet, is as close as we could get it to the pure concatenation of a request and a response, right? So it's as if we're simulating the round trip of I asked you for the acknowledgement and you turn around and ask me for the payload. I just assume that you're going to ask me for the payload, so I ask you for the acknowledgement and also here's the payload. But we're getting as close as we possibly can to only having one semantic over all of these interactions. And all you can do is ask for data that's bound in the namespace. All you can learn is more data that's bound in the namespace. But you do actually want to have efficient writes. And once we did this, still we haven't got at this stage to off-loom depacketization or other wins. We already reaped what to me were genuinely stunning wins from that exercise in autism. I really don't know how else to say it. Right? Just an irrational commitment to forcing every interaction that we could through the namespace. And yeah, the total rights in an interaction that would have been, I have a right, everything I send to you, you have a right, everything you received, you send me acknowledgments, I have a right for each of the acknowledgments. It's like, this is really expensive. It just goes down to, I want to send something to you. Well, that was initiated statefully, right? There was a right there. I will get an acknowledgement back from you when it's completely done, and I'll write that down. I have one right. And you will have a right for each response, right? So if I'm poking you with a big payload, I will write down the acknowledgement when that's all done. You'll write down all the pieces of the payload. But that in itself is already way more efficient than Ames ever was, and we haven't even gotten to the real win. Let's see, there's other things that we want to do. This we already did, this we shipped, it already happened. Okay, now let's double check the time.
It's done.
It's done.
It only took 26.
It only took 26 minutes.
Yeah. But wait. Yeah. So Joe, if you finish your talk here, then let's see if we can do a little bit better. Or are you already done?
It's 26 minutes for 130.
Yeah, so 130 megabytes, 26 minutes, 36 seconds. I don't know how slow that is, and I'm too embarrassed to calculate. So,
Somebody do the math on that.
Half a megabit. That's terrible.
Yeah.
My hard drive was 15 kilobytes a second.
Yeah, it's like 2 kilobytes per second.
Donald, how am I doing on time? When am I supposed to stop?
Yeah, we're just about on time now, so want to take a few
No, I'm not done yet. I just want to know how bad we're doing. All right, so that gets us through the history, the retrospective, the summary. This is what we've built. This is what exists. What I want to try to run through here, other than the constant, unending benefits reaped upon us by our irrational and total commitment to putting everything in the namespace, we achieved several things here that we have been trying in some way, shape, or form to do, and completely unsuccessfully for a while. So I'm sure everyone is familiar with a NOC jet, right? NOC is computationally infeasible on itself. We recognize well-known formulas, we accelerate them. It's great, it's sort of the whole point of Urbit, computationally speaking, from a certain perspective. We're thinking for just a second about what's actually nice about this, why it's important. It is superior to primops, built-in opcodes, FFI, because there's no semantic contamination in your base layer. You can accelerate the NOC, you have to get the same result as the NOC. The jet is formally not there in any way. It is a separation of mechanism and policy, always considered an important design constraint of any engineering effort. And it is so with arbitrary granularity. You can jet a whole big computation, punch out one little tiny corner of it, anywhere in between. This is wonderful. I wonder if it went over Finet. Oh, yeah, and then divide by 8. It's still fast. It's faster than it should have been. We were expecting 32 minutes, to be clear, so something was unexpectedly a little faster. Maybe. So it's something I have talked Ted's ear off about this literally for many years, is what does it look like to have a protocol jet? Jets are wonderful. How can we take, like you can't, okay? You can't have a protocol jet. You either speak the protocol or you don't speak the protocol. You're either there or you're not. The semantics are, enforced on one side or the other, right? They're in the formal layer, they're in the informal layer. You don't get a choice. Or you split the protocol, right? Of course, you can do that, but you're still speaking a protocol. It's like, how do you hide? How do you help out computationally, assist in the interactions of some protocol without taking responsibility for semantics, taking as little responsibility for semantics as you can? This has been a wonderful experience when it comes to pure computation. Is there any way that we can do anything like this in stateful computation? And so it's not a jet, but you put scare quotes around it. And we can say, when we're talking about I/O, when we're talking about a vein, what must be true? Arvo must control policy. Must is possibly going too far, but it should implement the default mechanism, right? You want the protocol to be meaningfully implemented formally. It's not impossible to not do this. In fact, all of you have used Urbit's HTTP client. Urbit's HTTP client does not do this. The vein is a scheduler. It says, I want to make an HTTP request. I will inform the runtime, I want to make an HTTP request. The runtime goes and makes an HTTP request. When there's a response, it injects it back in as an event. Urbit doesn't implement HTTP semantics. It just bridges to them. That's totally legitimate, doesn't break the model. Urbit's as wonderful as it was before. The HTTP client's kind of gay. It would be really sad if the Urbit network was kind of gay, right? No, it's not going to fly. So you want informal external code to be able to help, scare quotes, whatever that means, whatever it can accomplish. Take some of the load off of this protocol interaction without imposing semantics, or taking on responsibility. In the network in particular, what this means to me, I don't have to put my keys in the driver. The driver's C code next to a socket on the public internet. Is it impossible for us to write something where you put your keys there and you can trust it? No, it's not impossible. People do it. I really don't want to do it. I want my keys in Arvo. I want my trust base to be in Arvo. I'm going to blitz the slides. So this is the Merkle tree construction. This is what enables the degree to which this new networking protocol is kind of a protocol jet. We've split the responsibility, given more to the runtime than we ever have before without letting the runtime take over and while still maintaining the trust base inside of Arvo. So the way that we do this, this is ripped directly from the Blake 3 sister project, BOW. We have a Merkle tree. You do a depth-first traversal of the Merkle tree to deliver it to your counterparty. This enables incremental validation of the tree. You do that by sending pairs of children for each node. That lets you validate pairs of hashes, excuse me. Sorry, I'm in too deep. And in a serialized format, the hashes precede the data that they validate. So you basically just take the whole tree, do a depth-first traversal of it, hashes before data, serialize the whole thing, write it out. This is what the BOW project does. We looked at that and said, we can use this to take the authentication burden off of packets. But we don't want to stream. We're a network. Real networks are datagram-oriented. Sue me. What I mean by that, we don't want to use TCP. We don't want to have arbitrary chunk sizes. The correlation of, this sequence of bytes, how much of it is message, how much of it is metadata, we want those things to be explicitly sized. Which means we have to work at a cadence and you don't have these variable width properties. So we do the same thing, but we put the traversal over the packets. So instead of serializing the nodes of the tree and then some data, and you have these intermittent runs of hash tree data and then packet data, hash tree data, instead we just treat those as monotonic individual traversals and we put them together. So each packet is annotated with a pair of hashes. The pair of hashes doesn't correspond to the packet, it corresponds to the subsequent data that you will need for this incremental construction of the Merkle tree that you will use to validate the packet. So there's a layer of indirection there. The problem with this works, this is shipped. You will see it in just a second here. But the problem with it is that it does not resize well. It is, in fact, a highly scale variant because the traversals are not correlated. If you were to roll up the tree, right, you want to slice the bottom layers off of the Merkle tree. In other words, you want to talk about data in bigger chunks. You want to talk about bigger packets. Well, your traversal just sort of shifted around all over the place. And the data dependencies that you have in order to make that transformation are basically the full tree. It's possible there's a shortcut. We were never able to find a shortcut.
What's the optimal size? Or what size gives you the better?
So on the public internet, you cannot assume, legally, you cannot assume more than 578 bytes, I believe. But the specs are fake and that's not reality. Reality is everybody uses Ethernet. Ethernet has a frame size of 1,500 bytes. So if you're using IP, you take 8 bytes away from that. If you're using UDP, you take another 20 bytes away from that. You have 1,472 bytes at your disposal. There are standards for what they call path MTU, maximum transmission unit discovery, where you probe network paths, you send larger and larger chunks of data, you wait till it stops working, and you're like, I guess that was as large as it gets. It really sucks, and it's a terrible fit for NDN because we just said a second ago, data has a name, not a location. What's the path? What path are you probing? So NDN itself does hop-by-hop fragmentation and reassembly. And if anybody is interested and able to find the answer to this question, I would be really, really curious to know, for any protocol that does hop-by-hop fragmentation and reassembly, are they doing retransmission and guaranteed delivery then on intermediate nodes? Because otherwise you have this horrible colliding effect where packet loss between some relays that had to reassemble a whole large message is then loss of all incremental progress, and the loss propagates all the way back to you, where then you just make the same request again. And so I ruled that out very early. The path MTU discovery is super complicated. Also, we want to have a degree of flexibility there that it would take away from us. And so I said, all right, over the network, we're just going to stick to the standard MTU. We'll keep doing the same thing we've been doing. We're not going to try to send larger data over the network right now. But we made the packet format effectively arbitrarily sized. And the messages are effectively arbitrarily sized. And so you want to be able to send large packets. You want to be able to talk about very large pieces of data for alternative transports, if nothing else, right? For instance, again, 1,472 bytes over the public internet. If I'm talking over local loopback, that's 64K bytes, right? Over the LAN, it depends on what the LAN is. So we can't talk with a straight face about building for the future and a long-term strong foundation if we're gonna like bake the sizes into it. We have to be flexible with regards to the sizes. But then if you can't switch sizes, now you have this end-to-end problem of like everybody has to agree all the way along whatever path, which is a very late bound property, what actual path the data is going to go through. You really don't want to do, I believe it's like NP complete to like try to calculate the path ahead of time. You really, really don't want to be doing it. And if you're doing, even if you could do it, then your caches are like the worthfulness of your caches is degraded so substantially because I'm over here caching the packets at this size and then again at this other, and it's just like everything about it is really demoralizing, actually. And so we really, really wanted to make the rescaling work. And Ted did, and I still don't know how. So I sat for a long time this morning trying to figure out what to write for this line, and I settled on adjacent cousins. I actually don't know. Like, I know what the integer sequence is. I do not know how to describe this traversal. I do not know how to implement it through natural recursion, and I have tried many, many times. But this is scale invariant. This is not a joke. We are doing this. This is so beautiful. I can't even begin to tell you
Can you trace out
how beautiful this is. Yes.
you would get this in and how you verify as you go?
Yes.
Yeah.
So we start with the same thing as the verified streaming and the lockstep streaming. You need an initial Merkle proof to start. And it's actually not quite, it's one more thing than the initial Merkle proof. So you take the rightmost red nodes and then both leftmost pairs. That is your initial proof. That gives you everything that is in red. That means you know the root hash of the tree, so you can go off ahead and start validating a signature or an HMAC or whatever else you're going to do. We do not send the root. We do not send, if you know noun tree addressing, we do not send 1, 2, 4, or 8. We send 3, 5, 9, 16, and 17, right? But then
You send what you would need to do a Merkle inclusion proof to the leftmost
yes,
two leads.
yeah, and you have to send that first, obviously. That gets you started. So now, that is the first packet in sequence It is not packet 0. It is auth. We'll get to the overlay namespaces next, I promise. There are auth packets and data packets. So this is an authentication packet because of Merkle proof. It does not contain any data. We can guarantee that the proof will always fit. For arbitrary sizes of data, the proof will always fit in a single MTU-sized packet because our fragment numbers are 32 bits, log 32, 32-byte hashes.
How big are your fragments, Joe?
By default, they're 1 kilobyte.
That's 0 in your fragment size.
No. We use blocks. That's block 13. So after you send that initial proof, you send the first data packet corresponding to this node. To explain the tree real quick, these are kilobyte chunks of data overall in the message. The leaf nodes represent both the data and the hash of that data. The tree is the Blake3 tree. So if you just call Blake3 over the message, you get the root hash. Internally, for Blake3 to compute that hash, it had to hash each of the individual chunks and then roll them up, hash the siblings. That's how it computed the root hash. When you send a data packet here, you follow the dotted arrow to find the pair of hashes that you send along with it. Fragment 0, you're going to send the pair of hashes that correspond to this node. These two hashes here correspond to that node. The way to specify that is to say, you look at the subtree that this packet completes. You find the node of that subtree, and you skip one sibling and then get the 2 adjacent siblings. That is the specification. So this completes 0 subtrees, you send those 2. This completes 1 subtree, you send those 2 corresponding to that node. That was 1. Fragment 2 completes 0 subtrees, those hashes. Fragment 3 completes 2 subtrees. You send these 2 hashes. And so on. When you iterate this out, you find that the shape of the traversal is entirely scale invariant. You can just chop the bottom layer off of the tree. The sequence of interactions looks exactly the same. You can isolate an aligned subtree. The sequence of interactions still looks exactly the same. What this means is incredibly remarkable. To transform these 4 packets into 1 jumbo frame packet, we have no external data dependencies outside of the packet. We just concatenate their payloads together. That's the hash. By virtue of aligning which subtree you complete, right, that's the predicate that means that when you roll up, you already have everything that you need. Now, to go the other way, to take this and split it out, we also need this because, fragment 1 had these 2. Fragment 2 had these 2. Right? So in order to go down the tree, you need a pair of siblings. In order to go up the tree, you need to be aligned on a power of 2 sized subtree, and you have everything you need. You can just roll it up. This makes all of the size flexibility and claims about scope actually real. We're in fact ready, if anybody has an answer to my question, to do hop-by-hop fragmentation and reassembly. We could do path MTU discovery, but much more practically, we could do Ames over HTTP. We could do Ames over WebRTC. There's all kinds of things that we could do very, very soon. We can say that we are going to cache data in a size that is optimized for the storage medium, but still deliver the data in a different size. The driver can request data from the vein in a size that's optimized for the workload that it expects. And it can do it very efficiently because the vein serialized one packet. It didn't serialize 4,000 packets, it serialized one. Here's the best part. On the client side, as we receive the data, right? So when we spec this, we said we're going to assemble the whole message. Well, what do you think happens if you want to like send a terabyte message? You know, you malloc 1 terabyte. And then you send it over IPC, then you write it into a pipe, and then this is Urbit. You write it into your event log. So if you don't have any granularity there, right, you impose this end-to-end constraint on anything that's going to touch the data, that it be able to handle the maximum size. All right, I've said it. I'll keep talking about this, but it's time.
Yeah,
It's time.
okay. Wait, you said you're gonna keep talking and still you let...
Yeah,
Oh,
go ahead,
okay.
go ahead and do it.
Yeah, we have to put this though. Can you hold this? Hold my mic. Okay, let's see. Allow accessory to connect. So to recap what we did here, we read a 134 megabyte file from Clay using old Ames. I'm going to make all of this bigger soon. It took 26 minutes. Let me see. You have to hold my mic again, man. So, what we did here was using this hep read thing. I don't know if anybody knows what this is, but basically you can, this is like fake remote scry before Finet existed. It's slow, but this is what we did. We got the phase A, we got the file. Then after that, what I did here when messing around, I migrated, so it's pub reading from Nex. I migrated to new Ames, and let's see if this works. So instead of taking 26 minutes, it took 2.8 seconds. And I was going to talk some more, but Joe spoke way too long, so that's it. That's the demo.
So I will stop now. Thank you, Perry. The Blackman traversal is implemented. It's not yet integrated into what you just saw. That's our next primary focus. We need to make the routing real. There's little bits of polish to be done in various places. We're going to test the ever-living shit out of it. We're going to ship it. The only other thing I wanted to talk about today that I didn't get to was overlay namespaces, but you are all in luck. Tomorrow is going to be wall-to-wall shrubbery. The overlay namespaces are a key part of that design. They were theorized here in this effort. I'll be here all week. Find me if you want to hear more about it. Thank you all for your time.